So what are we going to do if we're dealing with an amino acid that is not nonpolar or that is not polar neutral? Like, what if we're dealing with an acidic amino acid and we're putting it into a weird pH environment? How will the pH affect that amino acid? So first of all, we're going to consider, just like we did up here with the nonpolar and polar neutral, we considered all three different options: when the pH was the PI, and when the pH was less than, and when the pH was greater than the PI. We're going to look at all those scenarios all over again. So for acidic amino acids, we've got one possibility when the pH is roughly equal to the PI. Now for acidic amino acids, the PI is not 7-ish. And so it's going to be a number that you'll be given, or if it's not given to you, you'll just go look it up and we'll practice doing that. And then we also have, at this time I want you to leave yourself a little bit more space, so 3 lines this time. We also have the option of when the pH is less than the PI. And what are we going to do in that case? And then we've got another option when the pH is greater than the PI and what we will do there. And then our fourth option is when the pH is way bigger, so much bigger than the PI. And we'll deal with that. Okay, so when the pH is approximately equal to the PI, which is not going to be 7, so if it's not given to you, we're going to look it up. But it doesn't really matter exactly what the pH is when we're making a general rule like this, because when the pH is roughly equal to the PI, we are a Zwitter ion. So that means that we are going to have the COO minus group, and we are going to have the NH3 plus group. We are going to be a Zwitter ion. Now, remember, what makes acidic amino acids, what makes them acidic, is that they have R groups that have an extra carboxylic acid part to it. So they have the amino acids acid, and that they also have the acid in their R group. So when the pH is roughly equal to the PI, the R group amino acid is going to be not charged. So it's going to be a COOH. And the charge on this guy overall is going to be the -1 from the acid part, and it's going to be +1 from the amino part, and it's going to be nothing from the R group because that's going to be uncharged. Overall, no charge. Overall, neutral charge. We'll look at some pictures of what that looks like. Actually, let's just jump right straight to it. Let's go straight to a picture. We're going to do, for our example, we are going to do aspartic acid. And we are going to draw it first at a pH that is equal to its PI. And we don't have to, like I said, we don't have to know exactly what that is. Actually, I'm going to give myself a little more space there. We don't have to know exactly what the PI is or the pH is. When we are at the PI, we are in full-on Zwitter ion form. So here is what this much of the amino acid looks like. And then to get the rest of the structure of aspartic acid, we're going to go to our table of amino acids and we're going to find it. Aspartic acid, which is right over here. This guy right here. Now, the tables of amino acids, pretty much every single one, no matter where you find it from, probably not exclusively, but almost all of them, they are always going to be listing the R group in the charged form. So down here, it's listing the R group as COO minus. And you have to be smart and realize that that's not allowed, not when you're at the PI. So our R group has to be CH2COOH. We have to draw it with that extra hydrogen on there because it is in the Zwitterion form. So what about our next possible situation? So the next situation is when the pH is less than the pI. When the pH is low, that means that we are dealing with an acidic solution, and that means that we are only allowed to see positive charges on our amino acid. So that means that we cannot see a COO minus group anywhere. So we need to have COOH. We also need to have that COOH group in the R group. So our R group also can't have a negative charge, COOH. And our amino group, that is allowed to still be at NH3+. That's okay. And so what will the charge be on this particular amino acid in this particular form? Well, we've got no charge from this group. We've got a +1 charge from this group. We've got no charge from this group. So the charge overall is going to be a +1 for this guy. And let's take a look at what that might actually look like. So let's draw aspartic acid at a pH of 1. We don't need to know what the pI is. That's a low pH. So when we're at a low pH, we know that we're okay with having positive charges. So our NH3+ is going to stay NH3+. We know that we're okay with having neutral, like you can have no charge. So our R group will stay neutral, CH2COOH. That COO minus, though, that's not allowed anymore. We've got to get rid of that minus charge. And the way that we get rid of the minus charge is by adding a hydrogen. So there's the structure of aspartic acid at a low pH. Let's keep going with this. What about next situation, when the pH is high? So the pH is greater than the pI. This would be a basic solution. And in a basic solution, we are allowed to have negative charges. So that means that if we're just looking at the amino and the acid part of the amino acid, we're allowed to have COO minus, but we're not allowed to have NH3+. We've got to convert that guy to the neutral version, which is NH2. Now, when our pH is above the pI, but not crazy above the pI, the R group is going to stay neutral. So the R group is going to stay COOH. And what's the charge here? We have a negative, we have a neutral, and we have a neutral. So this guy's charge is a -1. And let's draw aspartic acid at a pH that is greater than the pI. So let's draw it at, let's say we're going to draw it at a pH of 8. So we know at a pH of 8, we're not going to do anything to the R group. We are allowed to have the acid part of the amino acid be COO minus, but the amino part needs to be neutral. So instead of NH3+, we're just going to have NH2. Now for our last situation, we have the possibility of when the pH is really, really, really high. So this is going to be very basic. And we're going to see this happening at pHs above 10, at and above 10. And in this situation, we're going to be allowed to have negative charges, lots of negative charges. So we can have COO minus, that's going to be allowed. We cannot have an NH3+, so that guy needs to be NH2. It's so basic that our R group now is allowed to become charged. And so our R group is going to have COO minus. And what's our charge here? We have a -1, a neutral, and another -1. This guy's charge is going to be a -2 overall. -1 plus -1. And let's draw this structure. Let's say this is at a pH of 12, so that's way high, and that's above 10. And we know that we can have our COO minus. We know the amino group needs to be neutral, so that's NH2, no charge. And our R group, CH2, COO minus. Now, if you're not sure, if you're feeling uncertain about what to do with that R group, let's go back to our table. This table, for all of our acidic amino acids, it is drawing the R group in the extreme pH form. So it's showing you what the R group would look like in the most extreme pH. And that is also true for the basic amino acids. All of these R groups are drawn in the extreme pHs for our basic amino acids.